Alright, so let's go ahead and do the next example. So we're going to do example 5. Um, so example 5 asks us to evaluate the function y sine z along the curve c, where c is the circular helix given by the equation x equals cosine t, y equals sine t, z equals t, and the parameter is going from 0 to 2 pi. In this case, we're going to be using equation 9 from the book, which tells us that if we're going to integrate a function in terms of some variables along a curve, that we can put the function in terms of x, y, and z that have been parameterized for t, and then we have our familiar square root, which is our arc length. That's our infinitesimal bit of arc length times dt. So we're going to just follow along with that to answer this question. So in this case, our function f is in terms of x, y, and z, and it's equal to y sine z. If we write y and z in terms of the parameter so that they're restricted to follow along the curve, then we're going to get that this is sine t, so since that's y, and then sine t. And then we're going to have to figure out our arc length. So we need to know dx dt. So dx dt is actually negative sine t. dy dt is cosine t. dz dt is equal to 1. So that means that we're going to have, for our little infinitesimal bit of arc length, we're going to have negative sine t squared plus cosine t squared plus 1 dt. And that's going to be equal to the square root of 2 dt. So we can put this all together and we'll get that the integral over the curve c of our function f ds is equal to the integral from 0 to 2 pi, since that's what the parameter t is changing from, of sine squared t root 2 dt. We can, we're going to have to use a power reduction formula to integrate sine squared, so we're going to get root 2, the integral from 0 to 2 pi of 1 minus cosine 2t dt. This is something we've integrated a lot in the past, and actually this is over 2. And we're going to get root 2 pi.